Good afternoon, and welcome to today's webinar titled Process Heating Equipment and Related Applications, sponsored by PIC Heaters, Inc. Phil Sutter is the co-president of PIC Heaters, Inc. and has over 40 years of experience designing process heating systems for food and chemical processing, pulp and paper, energy, and various other industries. Today, he will walk you through the importance of a reliable process water heater and if a DSI system is right for you. I'll turn things over to him now for the main presentation.
Thank you, Stephanie. Welcome, everyone, and thanks for joining us. We're going to jump right into our presentation here, and we're talking to you today about process water heating applications and equipment. Just a little overview of our presentation. We're going to cover things like the markets and applications that we're involved with, types of heating devices. Now, this won't be all-inclusive, but this will cover kind of the basic heating devices on the market, the PIC heater itself, how it works, what it does, and then go through some process application details to talk about some of the more common applications in industry. So the markets typically served, and I'm going to preface this by saying PIC steam injection heaters are sold to industrial process applications. We don't handle any commercial, HVAC, residential applications. It's strictly industrial applications where steam is available. So the markets that we serve are food and beverage, chemical and pharmaceutical, pulp and paper, power generation, textile, and then there's general industrial applications that we deal with as well. Some of the common applications that we see across all of these markets are process water heating, jacketed vessel heating, and this could include reactor vessels, jacketed tanks, jacketed dryers, jacketed kettles, essentially any device that's jacketed and you circulate hot water for heating. We also deal with boiler feed water, and that serves a lot of industries because, as you know, you have to preheat the boiler water before you put it into the boiler. It makes it more efficient and doesn't shock the boiler. And then there's washdown and hose station heating that covers a couple different markets. CIP solution, which typically covers the food and pharmaceutical and some chemical. Starch cooking, and that can be done in two areas. That can be done industrially for paper mills for making paper, and it can be done in the food industry for food grade starch. Then there's batch tank filling, which covers almost all industries. Different types of slurry heating, pasteurizing products, either directly in line or through the use of, say, a plate heat exchanger to generate hot water through the plate heat exchanger. And then organic wastewater heating. Moving into the types of steam heating devices, we've kind of put this into three different categories. We start with kind of the simplest form, the form that I think of as the crudest form of steam injection is tank spargers, and they're used quite commonly. Then you have indirect heat exchangers, which can be both shell and tube and plate and frame or plate heat exchangers, and then inline direct steam injection or DSI heaters. So let's spend a little time talking about each one of those and go through the pros and cons of each. Starting with tank sparging. So as I mentioned, I think this is probably one of the crudest forms of steam injection. Oftentimes I see people just connecting a pipe into a tank, or even as simple as taking a steam hose and putting it in a tank. So it's simple to install and operate. Components are generally inexpensive. So you would find it used for heating boiler feed water tanks, big storage tanks, and silos. That's quite common in the pulp and paper industry, where they have silos with water coming back from all points of the plant and needing to reheat it. And then also heating cryogenic fluids. So some of the disadvantages you find in tank sparging applications is it doesn't offer very good temperature control. If you try to sense in one point, you may not see that same temperature in another point in the tank. So the temperature control accuracy is not very good. there's a lot of tank vibration, and that comes from steam hammer, from improper mixing of the steam bubble in the water, and that can seriously cause damage to equipment. So something you typically want to avoid. It's inefficient, and especially at elevated temperatures. Once you get in the 170 to 180 to even 200 degrees Fahrenheit range, that steam bubble has very small opportunity or reason for giving up its energy into the water. It usually goes right off the top of the tank, so can be very inefficient, sometimes upwards of 30% or more less efficient than direct steam injection. And then, of course, there's the extra time required to heat large volumes of water. So because of that inefficiency. Next, let's talk about shell and tube heat exchangers, the indirect method. So advantages being that they're typically inexpensive, especially with a copper tube bundle. They're quiet. There's typically no sound generated from indirect shell and tube heat exchangers, and they can operate on low pressure steam. Oftentimes they're sized for that 8 to 10 to 12 psi steam pressure range. They do have to get bigger because of that lower pressure steam, but they can handle that because the steam is not in direct contact with the water. And then lastly, once that steam condenses inside the heat exchanger, that condensate is returned back to the boiler for reheating. So some of the disadvantages associated with shell and tube heat exchangers are they do consume a lot of floor space. And as I mentioned earlier, that if you do run on lower pressure steam, that 15, 30, even lower pressure steam, you need to add surface area to that shell and tube heat exchanger to get the same heat transfer rate. So everything gets much larger. The diameter gets bigger and the length gets bigger. So that's where you take up a lot of floor space. And they can be difficult to clean. So if you have to take that tube bundle out, you have to have room on the exterior side or where the bundle is to remove that tube bundle. Response time. So if there are process changes, water flow rate either increases or decreases, the heat exchanger is a lot slower than a direct steam injection heater to respond to those process changes. And lastly, it's less efficient than direct steam injection. A heat exchanger only uses the latent heat available in the steam energy. The sensible heat is not used, so there is some efficiency loss in that use of the latent heat. Another type of heat exchanger are plate heat exchangers. So the advantages being that they, again, are quiet. They can operate on low pressure steam. They consume less floor space than that shell and tube heat exchanger. And plates can be added or subtracted to adjust for surface area and capacity. So it makes them kind of a natural fit for applications where you might have to change the process conditions later on, either by adding or subtracting plates. Some of the disadvantages with this type of plate heat exchanger are, of course, they can get expensive. So there's some difficult to clean. So if you have to clean them, obviously the end has to be pulled off and all the plates have to be separated and cleaned or disinfected. So it's a time-consuming process. Gaskets that are used can't withstand high pressure steam. So I know sometimes it is employed to plate heat exchangers. I have seen them in the field where there's a shroud put over the plate heat exchanger because they're leaking due to the use of high pressure steam. So high pressure steam comes with its disadvantages to these gaskets, that the gaskets that just don't withstand those pressures and temperatures. And then, of course, you're only using, again, the latent heat energy in the steam, so they're less efficient than direct steam injection heaters. So now moving on to inline direct steam injection heaters. It's the most efficient use of steam energy, so you are using both the latent and the sensible heat in the steam. So right there you've got an energy advantage. They oftentimes can pay for themselves in a short time frame. Compact size. They don't occupy much space at all, a lot less than a heat exchanger. So they're, I don't want to say half the size, but they're generally quite a bit smaller than a shell and tube of comparable size or capacity. They are also very responsive to process changes, so things move pretty quickly through them and are sensed very quickly. So the heater can either ramp up or it can shut down within a matter of seconds to respond to those changes in process conditions. And that in turn leads to very accurate temperature control. So if you can adapt quickly to those changes, you can very easily or typically maintain it like plus or minus 1 degree C temperature accuracy. There are, of course, obstacles or disadvantages to steam injection. First one being dilution. You are condensing that steam right into the water or liquid being heated, and sometimes that's not acceptable for all liquids. If there's oils or food products or certain other chemicals or pharmaceuticals where you cannot dilute them, obviously steam injection would not be a good choice here. Steam injection also requires medium to high pressure steam. This device can work probably as low as maybe 20, 15 psi at best on the low end. So that's better suited for the indirect heat exchangers. Where these devices shine is in the 50, 100, 150, sometimes even 300 psi steam pressures. Typically by design, the steam pressure must always exceed the liquid pressure, generally by 20 psi or more. That's because you have a steam control valve that regulates the amount of steam upstream of this device, and then there's a slight internal, like a 10 psi drop internally in the injector. So that's where the 20 psi differential comes from. So if you have 50 psi water and 100 psi steam, we've already got a 50 psi differential, so that would be perfect for a steam injection application. Next would be contamination. If your boiler chemicals are not safe for mixing with the water, it's not advisable to use steam injection, but it is very common in all process industries. But in the food industry in particular, those chemicals must be FDA or USD approved. So if you are heating potable water with this device and your boiler chemicals are FDA approved, the hot water leaving this unit is still considered potable. With this device, there's no condensate return. That condensate is consumed. It becomes part of the water that's going to your process. So that will require some additional, a slight amount of makeup water at the boiler. So next, talking about the PIC steam injection heater itself. The theory of operation here is, and if you could, everybody can see this diagram, the steam control valve, which is item number 3, modulates the steam flow into the PIC heater body, which is item number 4, in response to the temperature control signal. So if you have a temperature set point at item 2, the temperature controller, and then you also have a temperature sensor, item 6, that's going to sense the water that's leaving the unit. So maybe to back up a little bit, the cold water is entering at the bottom of the unit at number 1. The steam is entering from the left side where the Y strainer and pressure gauge is shown, and then hot water discharges at item 5, leaving the unit. So it's a very compact inline device. And this temperature controller can either be a local pneumatic controller, which can be quite simple but effective, or it could be a local electronic controller that an operator can operate or manipulate up and down, change temperatures, or you can even go to a plant DCS or PLC to do your temperature control from a control room. So the kind of principle of operation for this device, again, looking at the cutaway drawing on the far right side, the cold water enters on the bottom where it's a purplish color. The steam is entering the side where it's red, and the hot liquid is leaving the heater where it's orange, so the steam is already mixed. So that steam is injected into and blended with the liquid that's being heated, and this is all happening inside that chamber. And with steam injection, all the available energy, or BTUs, from the steam are used to heat the liquid. So those steam bubbles then are immediately mixed with the liquid inside the chamber, and there's mixing vanes that we call helical flights that help add turbulence, a slight amount of turbulence to that cold water and the steam, so that it mixes right then and there inside that chamber. So by the time the water leaves the PIC heater or this chamber, all of the steam bubbles are fully condensed, and you can sense the temperature immediately downstream of the heater. And you want to do that because steam injection is a very fast-acting system. You put the steam in, you want to sense the temperature right away, and you can make adjustments with the temperature controller and modulating steam valve accordingly. So again, as I mentioned earlier, the steam pressure must always exceed the liquid pressure for injection to take place. So normally we like to see 20 psi or more differential. So advantages of this type of steam injection heater are, first of all, turn down capability. This is the widest operating range of any steam injector on the market. Standard steam flow turn down is about 12 to 1 with a single steam control valve, and capabilities up to turn down of 100 to 1, where we pipe two control valves in parallel with what we call dual steam control valves. Another advantage being low noise level. So with steam injection, you do have some sound generated, typically a hissing sound. Because the steam is broken up into a fine bubbles or fine mist through hundreds or thousands of small orifices, there's not a lot of sound generated. So normal sound levels are 85 dBA or lower, which is far superior to Venturi or choke flow heaters, which can be a very loud operation due to taking a high pressure drop across them. So basically sonic velocities generate a lot of noise. Next, there's a low liquid pressure drop across this device. Typically doesn't exceed 1 psi under normal flow rates and pipe sizes. It offers precise temperature control, plus or minus 1 degree C, with an electronic temperature controller. With a pneumatic temperature controller, you may not see quite that tight a temperature control, but many plants are moving to electronic temperature controls these days. And then energy efficiency. Because you're using all the BTUs in the steam, the fuel savings can be upwards of 28% more as compared to indirect heat exchangers. So the PIC heater products that are on the market are, starting with our constant flow design, that's recommended for applications where the liquid flow is typically fixed or subjected to minor variations, like maybe a 2 to 1 turn down or even 3 to 1 turn down. So water flows to a tank or to a process, but there's very little changes in flow rate. So this constant flow design is very well suited for that application. Another type of product available is the variable flow design. So that's used when the water flow varies over a wide span or is subjected to frequent or random on-off cycling. So if you're filling tanks on and off, or you're heating water for hoses or plant sanitation, that's going to be a constant and varying or a continuously varying flow rate. And this design has an inline pump that provides circulation through the housing, and that maintains very accurate temperature control over those varying flow rates. So that's a little more equipment to the device, but still offering all the advantages of steam injection, including accurate temperature control. Other available products are the SC sanitary design, and that's for heating or cooking any food-grade water miscible liquid or slurry instantly on a continuous straight-through basis. So this is quite often used for food products. A lot of food that's processed has to be heated or pasteurized, and this is a preferred choice for inline product cooking. It's also used for CIP heating or even nitrogen gas injection. So where customers want to try to displace any oxygen that's in a food product, they can inject nitrogen to help displace that oxygen. And it gives the product a much better appearance too. Another design of industrial heaters is the BX slurry and mash heater design. So this as well provides instantaneous and complete cooking of starch products. This is very prominent in the paper industry. So where they have to cook starches for coating papers, and it's also used for heating other water miscible slurries. It can also be a great choice for viscous slurries such as waste grease and oil. So two not so common applications, but it's something that we took on a little while ago, and it's picking up nicely. So good application for a PIC steam injection heater. There are also specialty fabricated designs. So this employs the same trusted features and benefits of our standard models, but when the flow rates get very large, for instance, upwards of even 25,000 gallons per minute, or the pressures that are involved are very high, 900, 1,000 psi are not uncommon, or materials and constructions that are required, like Hastelloy, titanium, Inconel. That can be fabricated and is used with this design, which is different from our standard design. So we can step away from the standard design, get something really big if need be, and make it work for your applications. Then we can also take this another step where we can build packaged process heating systems. So we offer these packaged heating systems, first of all, with our steam injection heating systems, or where steam injection isn't allowed based on the objections we talked about. We will employ other methods of heat transfer. So if there are times where a shell and tube is better, or a plate heat exchanger, or we've even done electric heaters, then we look to our division called PIC Custom Design. So we use our same packaging expertise, and we put together designs where they typically wouldn't be used for a steam injection heater. So each design, whether it be steam injection or our PCD division, is custom engineered. So that satisfies any specific customer requirements. Some of you might have piping requirements or specifications. We have no problem with those. We can take a look at those and build a skid that complies with your requirements. And this can all be done on a very compact skid or module. So moving on to some of the other application details within each industry. So starting with the food industry, which is a very large industry for us. We often see heating process water for plants, wash down hose stations, so plant sanitation is a very large application for us. And that's where that variable flow heater is used. Batch tank filling, again, very common application. A lot of people use it and need it. Then you can get into your closed loop applications, for instance, for a pasteurizer. So if someone wants to pasteurize ice cream, for instance, obviously you can't mix the steam or the condensed water into the ice cream, so you put the ice cream on one side of a plate heat exchanger and circulate hot water through the other side and pasteurize the ice cream prior to packaging. Also jacketed tank heating, so a similar closed loop application where you're heating a product in a tank. Maybe it's a soup or stew or gumbo or something like that. Hot water can be used and circulated through that jacket. CIP solution, another very common application for DSI heaters. Next is oil and grease heating applications, where they're doing oil recovery. They want to separate any solids out of there, so steam injection heating is a very fast and accurate way of heating that waste grease or oil. Vegetable blancher is another great application where if it's large, usually tremendous flow rates of water, maybe 1,000, 1,500, 2,000 gallons per minute. So we've got the heaters that can be used in this type of application. And then there's inline product cooking, and that can be various different food products from baby food to pet food to ketchups and sauces, a lot of starch products. So very common application for a steam injection, a sanitary or SC type steam injection heater. That's the food industry. Now moving into chemical and pharmaceutical industrial applications. Heating reactor vessels is a very good and common applications for chemical and pharmaceuticals. So where you're making a reaction, that's typically done in a vessel that has a jacket around it. And hot water can be circulated around that jacket. It has many, many advantages over using steam or heat transfer fluids because hot water can evenly heat that reactor vessel instead of having hot spots from steam and dealing with getting rid of that excess condensate after it's condensed. So circulating water is a natural fit for that. Again, heating process water, various types of slurry heating, batch tank filling, other closed loop applications could be a plate heat exchanger. So where there's a pharmaceutical product on one side of the plate heat exchanger, hot water can be circulated in the closed loop. And we're not limited to just temperatures to 100 degrees C or 212. So if you elevate the pressure in that loop, we can quite easily get temperatures approaching 300 degrees Fahrenheit as long as that steam pressure, again, is at least 20 psi above that loop pressure. So, given all the process conditions, we can size that through you and look through that. So we do provide data sheets with each application. I ask you to fill out data sheets, and it's engineered by the rep or the factory, and information is sent on that particular recommendation. Also, organic wastewater treatment is a common application in this industry, and in many industries as it is. And then in chemical and pharmaceutical, also they sometimes just need tempered water. So steam injection heating is a great source of piece of equipment for that tempered water heating. Next, another market that's quite common for steam injection heaters is the pulp and paper industry. They do a lot of starch cooking. I think I mentioned earlier for coating paper that steam injection cooking is very rapid and it's very accurate. They also do a lot of mill water heating where hot water is used throughout the mill. There are different also machine showers, felt showers, Fourdrinier showers, and accurate temperature control is kind of one of the reasons why paper mills often choose a steam injection heater for those types of showers. So batch tank filling, like hydropulpers, require hot water. Then you move on to other applications like green liquor heating and whitewater heating. And lastly, brown stock washer. We supply hot water to the spray nozzles on the brown stock washer. So that's just a little bit touching a few applications in the pulp and paper industry. Also, we serve the power industry. So, for instance, in coal-fired plants where there's FGD or flue gas desulfurization is required, they'll have a lime slaker and they need hot water for the lime slaker. So, steam injection heater is a great fit for there. We also do condensate mixing. So where you might have various pressures and temperatures of condensate that come back from other sources in the plant. Oftentimes, plants like to just mix those in a tea or a common place, but due to flashing that may happen, you can have a lot of hammer and vibration. We can solve that by putting in one of our PIC heaters in place of that mixing tea. Then you've got also Hercigs or heat recovery steam generators that when they've been down, they need a quick startup. So a PIC heater is a great application for starting those units back up. Boiler feed water, as I mentioned, this can cover all markets because that boiler feeder water has to be heated, but especially in the power industry. Then there's also resin bed regeneration and reverse osmosis water. And reverse osmosis is done in many industries as well. But in the winter or cold weather months where you just need to temper that water up, maybe just to 55 to 75 degrees Fahrenheit, and the accurate temperature control from a steam injection device is far superior to any heat exchanger that might be varying plus or minus a couple of degrees. So heating RO water is a great application for a PIC heater. And then other industrial applications that we've tackled over the years, anything from oil sludge heating, where they're reclaiming oil from large tanks, tank car cleaning, and also including tank car heating. So two common applications where, again, during the cold weather months, heating and cleaning are an advantage, and steam injection is very quick at the point of cleaning. Organic wastewater is done in a lot of industrial applications. Parts washers. So, for instance, in the automotive industry, where you're making gears and parts for engines and transmissions, those parts, they're using a lot of cutting fluid, and that cutting fluid, well, I guess that gets into wastewater heating, but with the parts washers, they like to wash off those parts very quickly after they're machined. So using a steam injection heater, great application. We're also used quite often in steel mills and textile mills for generating their hot water. Trap grease heating to reclaim all the grease from restaurants and from French fry heating and deep fry heating. That gets collected by companies that's all they do is collect all that grease, and to reclaim it and separate it. Heating it is a very effective way of doing that. And then we've also seen use from industrial laundries. But again, as I mentioned earlier in the presentation, most of our applications, I should say all of our applications, are strictly industrial, so no commercial, HVAC, or residential applications. But I hope you've enjoyed our presentation here. Thank you for joining us today.